Hello everyone, I am Vlad and together with my colleagues Edward, Ariane and Radu would like to present ExDDV, a new dataset for explainable deepfake detection in videos. This is a joint work between the University of Bucharest and West University of Timișoara. The core idea is simple. Existing deepfake detectors tell you whether a video is fake, but not why or where. We aim to address this point. The threat from deepfake is growing fast. A recent forensics report found that deepfake-based identity fraud nearly doubled between 2022 and 2024 from 29 to 49% of fraud cases. This is being driven by increasingly powerful diffusion models that produce videos almost indistinguishable from reality. Current automatic detectors have two big problems. They fail to generalize to new generative models they haven't seen during training, and crucially, they give no explanation for their decisions. Users are left with a binary verdict and no insight into what to look for. To address this, we introduced ExDDV, the first benchmark specifically designed for explainable deepfake detection in video. What makes it unique is 3 layers of annotations. First, text descriptions, human written explanations of the specific artifacts in each video, things like eye jitter, mouth smearing, or blurry skin texture. Second, click annotations. The annotator clicks directly on the artifact location in the frame, giving that pixel level localization. Third, difficulty levels. Each deepfake is rated easy, medium, or hard, enabling difficulty-aware training down the line. ExDDV aggregates videos from 4 well-known sources: Deeper Forensics, Face Forensics++, the Deepfake Detection Challenge, and BODPAV. This gives us coverage across a wide range of generative methods, from face swap techniques like face swap and face shifter to more recent diffusion-based approaches. In total, the dataset contains 5,369 videos, 1,000 real and 4,369 fake. We provide an official train-val test split of 4,380, 482 and 485 videos respectively, so results are directly comparable across future work. All annotations were produced by 2 paid expert annotators working independently. We built a custom graphical user interface from scratch for this purpose and applied automatic spell checking and language normalization in post-processing. Each dataset is equally split into subsets such that each method and each possible kind of visual issue is described from 2 distinct points of view. The dataset provides a description of the artifacts, their location, the difficulty, and to identify them. Here, we provide some examples of annotation. The textual descriptions are below each picture and the green dots indicate artifact locations. The border color indicates the difficulty level: green, easy, orange, medium, and red, hard. We notice that there is a wide range of artifacts: blur, white anomalous spots, or skin deformations. To measure consistency, we gave both annotators 100 identical videos and compared their outputs. The sentence burst similarity of 0.62 confirms strong semantic agreement. The annotators are describing the same artifacts even if they use different words, which explains why lexical metrics like blur are lower. For clicks, over 53% of annotations pairs fall within a 2-second and 75 pixel window of each other, a strong level of spatial temporal agreement for this kind of subjective task. We evaluate 3 vision language models families on ExDDV. Blip2 uses a frozen image encoder and a lightweight Q-former to efficiently bridge vision and language. 5-3 Vision takes a data-centric approach, relying on carefully curated training data rather than raw scale. And Lava 1.5 projects visual features directly into the LLM token space using a linear transform. For each model, we test 3 training regimes: 0 shot with a fixed prompt, few shot in context learning using KNN retrieved examples, and full fine-tuning with LoRa for the larger models. Rather than fine-tuning the model, in-context learning tries to guide it purely through the prompt. Here's how our pipeline works. For a given test video, we extract a future embedding from its middle frame using a clip-based ResNet encoder. We then search the training set for the k-most visually similar frames using cosine similarity and retrieve their human-written annotations. These annotations are injected directly into the prompt as examples, essentially telling the model, here are some explanations for visually similar videos, now produce something similar for this one. We found k equal to 5 and high-level ResNet features to work best. The appeal of this approach is that it requires no weight updates at all. You can swap in new examples at inference time. The downside, as we'll see in the results, is that it's outperformed by fine-tuning and the retrieved examples don't always transfer cleanly to a new video-specific artifact. Fine-tuning gives the best model a chance to actually internalize the language patterns and observations of annotators. For BLIP2, we follow standard fine-tuning, while for the larger models, Phi3 Vision and Lava 1.5, we use LoRa to keep memory requirements manageable. Rather than feeding a single frame, we sample equally spaced frames across the video to give the model a temporal sense of the content. We experimented with more elaborate prompts but saw no meaningful difference, so we kept it minimal. What is wrong in the images? All models are trained for 10 epochs with ADMW. This setup consistently yields the strongest results across all three model families. Here's how we use the click annotations at training and inference time. Input frames are extracted at equal intervals from the video. A vid-based regression model pre-trained on ImageNet predicts XY coordinates of the artifact location. We then apply a masking operation to focus the VLM's attention on that region. We test two variants. Hard masking zeroes out everything outside the 75 pixel radius around the click, while soft masking applies a Gaussian fall-off centered on the click. The vid predictor achieves a mean absolute error of 0.055, which is roughly 12 pixels, which is quite precise for unconstrained video frames. The results tell a clear story. Fine-tuning dramatically outperforms both pre-trained and in-context learning across all three models. The best overall sentence BERT score is 0.55, achieved by BLIP2 fine-tuned with hard masking. Click supervision consistently helps, adding masking boosts every model. Interestingly, hard and soft masking perform similarly, so the key factor is simply directing the model's attention to the right region. In this plot, we showcase the performance of fine-tuned Lava model for different dimensions of the training set. The performance reaches a plateau after 2000 training samples, and this observation suggests that our dataset contains enough sample to train an explainable deepfake detection model. This figure contains a comprehensive diagram with qualitative samples for all the training scenarios applied on Lava. These examples include both relevant explanations as well as wrong explanations, such as identifying artifacts on real videos. In this figure, we showcase some examples of how the vid-based click predictor compares with the ground truth click locations. We observed that the predictor is able to precisely locate visual artifacts. To summarize, we've introduced ExDDV, the first dataset to pair deepfake detection videos with both textual explanations and spatial click annotations. We've benchmarked 9 model configurations and shown that fine-tuning with click supervision produces the best explainable outputs. Looking ahead, we plan to exploit the difficulty labels, for example, through curriculum learning, to push the model performance further. We hope ExDDV serves as a foundation for the next generation of transparent, trustworthy deepfake detection systems. The dataset and code are publicly available at the GitHub link shown. We thank you very much for showing interest in our work.